Our last speaker, who's going to help us close our workshop, is a distinguished colleague, Professor Sangwon Suh, at the Brand School here at UCSB, who is a well-known expert on life cycle assessment and industrial ecology. He's going to tell us about his recent work, with his group, about how data centers can support a renewable energy integration in electricity markets. So with that, Sangwon.
Thank you, Manoj, for your kind introduction. I'm very pleased to present our recent research paper. Just got published. At the end of this presentation, there's a link to the free copy of this article, so stay tuned. I would like to acknowledge my co-authors, Jia Chang, who is working with me as a PhD student, and she did most of the work, as you can imagine, that I will be presenting. And Andrew Chin, actually, he was presenting at the IEE seminar about a couple of years ago, and that's how we were connected. And he is from the University of Chicago. And this is a collaboration with both of them. So let's start with the variable renewable energy. As we all know, variable renewable energy is growing rapidly. In California, especially, as you can see, there is a quite significant growth in solar and wind renewable energy sector in recent years. And the growth is set to even further extend under the renewable portfolio standard targets. So by 2030, we are expecting to have about 60% of our electricity coming from variable renewable energy. Currently, it's about 30%. We are kind of slightly overachieving that 30% target. So the problem of increasing the variable renewable energy in the grid is that, well, there's a problem called curtailment. I think many of us are familiar with the curtailment, but for those who are not, I would like to kind of introduce what the curtailment that we are talking about. So let's say here is a, let's say, typical load profile, supply and demand profile of electricity, where this yellow marked, yellow colors, these are PVs, photovoltaics. And as you know, natural gas power plant, they can modulate their output. They can increase or decrease to a certain extent. And coal power plant, to my understanding, is much more difficult to modulate the output, especially they cannot completely turn off. So even if there is a lower demand during the time when renewable energy is pumping out this electricity, it cannot go down to zero. This is fine until renewable energy portion in the grid is up to a certain level, but as it grows, there will be the case from time to time when the supply of electricity from variable renewable energy exceed the total demand. So in that case, what we are seeing in this red zone here is a curtailment, meaning that this is excess electricity that does not have the demand that matching with the production. So this is called curtailment. In basically what happened is that utility companies are shutting down, basically not receiving those electricity or not producing those electricity, or we are worse, we are selling that excess electricity at negative cost. Basically, we are bearing the cost at the same time transmitting those electricity to our neighboring balancing authorities. In recent years, as our renewable energy portion in the grid grows, the curtailment also grew. So what you are seeing here is that in 2020, this red bar, dark red bar, shows the amount of curtailment per month. So as you can see, generally April, May, to my understanding, is the highest curtailment month. And we have seen the highest curtailment in history in California. And that is partly due to the COVID-19 as well, to my understanding. But as our portion of the renewable energy in the grid increases, there is a speculation that probably curtailment problem is also growing. So this is the annual curtailment in Kaizo, but on a daily basis. So annual curtailment in 2015 was only 188 gigawatt hour, and it grew all the way to about 460 gigawatt hour in 2018, and 2019 last year it doubled the amount. So fairly significant growth in curtailment, as you can see. And this is interesting because in California, as you will know, we are paying a bit more to electricity. In 2019 report just released, to my understanding, we are paying about 55% higher price for electrics as compared to national average. So if I just convert 2019 curtailment to retail price of about 20 cents per kilowatt hour, which is about the average of the California ratepayers paying for the electricity, is about $200 million worth of electricity that we are curtailing in 2019. So when I faced these figures, I thought that, well, this does not make sense to me. A larger amount of electricity is either wasted or sold at a negative price to our neighbors from the state where electricity price is one of the highest in the nation. And the problem is set to grow. So obviously, there are a lot of people working on addressing this curtailment problem. For example, as Southern California Edison also working on this, and the PG&E working on this. We are putting a lot of grid scale battery storage, and there are more to come in the plan. And we are talking about lithium ion batteries and some working on flow batteries. Another strategy to solve this curtailment problem is to expand the transmission lines. So that is basically about moving watts. So when there is excess electricity, we are transmitting to other neighboring grid authorities by expansion of the transmission lines. Another approach is to use the excess electricity to produce some storable or durable goods or energy carrier, so that whenever you have excess electricity, you produce them and then you can ship it to the destination where the demand is later. Because as we know, storing electricity is quite expensive. But all these options come with its own limitations. For example, batteries is still quite expensive, and expansion of transmission lines is quite expensive, and long distance transmission, we also have transmission losses. Aluminum is quite bulky and heavy, and transportation and storage is quite costly. Pumped hydro is limited by geographical spaces, and hydrogen is the lightest, least dense material that we know of, and we already have a lot of difficulties in transporting hydrogen in longer distance. So these are the limitations of the current strategies to resolve the curtailment problem. So what we were thinking of was to use data centers as a kind of storage device, and this is how we are thinking. So energy consumption by data centers is also set to grow. This is the forecast that published in 2018. By 2030, we will be seeing a lot more than double of the energy consumed by for the information, and part of a significant portion of the growth is coming from the data centers, and this is also data centers. The good thing about data, instead of moving electricity, we can move data much more easily and cost effectively, because we already have established quite substantial infrastructure for fiber optics, and there's information highway basically throughout the country. So instead of moving kilowatts, we can move bits. And what this animation is showing is Twitter activities as the population wakes up. So as you can see, as people wake up, they start to tweet, and this is just one example. But what it shows is that the demand on data processing and data transmission is not homogeneous. It's very heterogeneous around the clock. So what that means is that data center load is not always in maximum capacity. So there is ups and downs in data center load. So the question is, can we use some of the slack capacity to process the data migrated from other data centers using excess electricity and transmit back the result of the processed data to the destinations where those processed data are needed? So that was the idea. And as it turns out, the data centers are not necessarily located in the areas where the electricity is the most carbon intensive. So some of the areas where data centers are located are very carbon intensive areas. For example, the PJM area, including West Virginia, we know that they're very cold heavy electricity. They have very high concentration of large data centers. So the idea is, again, using the excess electricity for data processing jobs transferred from other regions where electricity should be generated at cost. And this is the title, Moving Bits, Not Watts. So let's look at this rather complicated diagram. So let me explain what this is. So let's first look at the pink envelope here with a clear black line. That is the total amount of energy consumed by data centers. So you can see this. This is for 1 week. There is a daily pattern, but also during the weekdays versus weekend there is a difference, right? And data centers are using electricity not only for server activities but also non-server activities such as cooling. But as you can see, not any given time, at any given time, data centers are not really reaching its full capacity. There's ups and downs, so there's always kind of a slack capacity available. So this is one of the days of 2019 that we analyzed based on the excess electricity that we had available. What if we augmented the processing of data in Kaizo region to the extent that we can reach about 70% of the total capacity? So it is not always so, sometimes the capacity is not available. Then even if there is excess electricity, we cannot use that excess electricity. Sometimes there is a select capacity, but there is no excess electricity. So it's not always that we can fill this white space. So this is one of the many days, one of the 365 days we analyzed. And you can see it's not, filling up the entire gap, but sporadically here and there, we are filling some part of the gaps there. In this particular example, we analyzed the case of migrating data processing job from PJM to Kaizo, and this is the carbon intensity figure that was published elsewhere and from PNAS. And as you can see, PJM happens to have much higher carbon intensity as compared to Kaizo. So migrating data processing jobs from PJM to Kaizo potentially, we thought, reduce not only the curtailment in Kaizo, but also overall greenhouse gas emissions by displacing carbon intensive electricity used by low carbon intensive electricity in Kaizo. So just in summary, the question that we were asking is, what is the potential of migrating workloads between data centers in reducing renewable curtailment, and how much greenhouse gas emissions can it reduce? So here is the result. I mean, we analyzed quite a bit of data, including, for example, hourly curtailment in Kaizo in 2019. This is day by day and hour by hour. This is the 0 to 24 hours, and this is January 1st to December 31st. And we mapped that out with the hour by hour carbon intensity of electricity in PJM versus hour by hour carbon intensity of Kaizo. And we simulated the case of migrating the load from PJM to Kaizo during the time of excess electricity, also when there is a slack capacity in the servers located in Kaizo. So using existing data center infrastructure, not building new ones. That was our start, and we also analyzed what if we build additional capacity in Kaizo to absorb even more data processing jobs. So fast forward, this is a result. It's a bit complicated, so I will put a little bit of time to explain what this is. So obviously, the amount of the excess electricity, the curtailment absorption, depends on the maximum server utilization rate. And we believe that, in an ideal situation, it can reach probably 80–85% of server utilization rate. Rarely it can go beyond 90% to our understanding. Also, it is a function of additional data center capacity, right? So let's look at the zero value for the additional data center capacity. So without building any additional data centers, what you can see here is that we can already reduce about 50% of the curtailment. This is black line here at around 77–78% of server utilization rate. And the color in the background indicate the net greenhouse gas emissions at that level. So we can reduce already quite significant amount of greenhouse gas emissions. These are the kiloton CO2 equivalent greenhouse gas emissions. So it's about, at this point, I would say this is, let me see, about 190 kilotons of greenhouse gas emissions. And what is interesting is that if we add additional data centers, of course, we can absorb more. As you can see, 50% again can go up to 80%. However, at the same time, there is a nonlinear response in terms of the amount of greenhouse gas emissions reduced. That is because the additional data centers will also require greenhouse gas emissions to produce them. So this is life cycle study. So we have included life cycle emissions to produce those data center devices, equipment, and construction. So this is the greenhouse gas emissions result, and this is abatement cost result. So we also analyzed the potential cost associated with absorbing additional data processing jobs. And this is again the function of maximum server utilization rate and additional data center capacity. What I want you to pay attention to is this zero line. This zero line means that, well, below this zero line, basically, this solution, moving bits rather than watts, will save cost while reducing greenhouse gas emissions. So in summary, the result shows that the load migration within the existing data center capacity during the curtailment hours in CAISO has the potential to reduce 113 to about 240 kiloton of CO2 per year. That was based on 2019 data, and absorb up to 62% of the total curtailment with negative abatement cost in 2019, of course, depending on the server utilization rate. It is also possible, according to our analysis, to absorb up to 77–79% excess DRE while still managing to keep the net abatement costs negative. So this is, in a way, kind of simulation results. It's a more theoretical exercise, and there are obviously a lot of challenges. There are reasons why this is not happening already. So one of the challenges is that we need fluid communication and control among variable renewable energy generators and independent system operators, as well as data centers, and we don't have that yet. And also, there should be a mechanism to share the benefits among parties. And currently, there are silos, and even if they're working together, we'll be able to generate benefits. There is no mechanism to share that benefit. That's one of the reasons why this is not happening. And I think that we also found that there are some contractual obligations that may be along the way, which is that, well, the service level agreement by the data centers specify the delays that they can tolerate, and transmitting data processing jobs to CAISO and coming back may violate some of those contractual obligations. And obviously, there are some data processing jobs that are not urgent, and those asynchronous jobs would be the first target for this type of arrangement. What is also key to this type of solution is the ability to accurately forecast variable renewable energy output. And if we cannot do that, then, well, we don't know when to migrate data processing jobs and when not to migrate data processing jobs. And there are some progresses in this direction. And what I'm showing at the bottom of this slide is the results from the Adam grant from from Stanford, who was also a guest speaker at IEE seminar about a year ago. He developed the algorithm using machine learning and artificial intelligence to have a short-term forecast of renewable energy generation, just using the camera to look into the sky. And his team was able to come up with a fairly robust algorithm to forecast the renewable energy generation, short-term forecast. So through those development, I believe that, well, there is a potential. So what we have analyzed, which is the potential to reduce greenhouse gas emissions as well as the cost and minimize the curtailment. So this is the QR code. If you have a camera, you can just scan this and it will lead you to the free copy of this article. Just publish it. And I would like to again acknowledge my co-authors, Jaja and Andrew. Jaja especially did all the great analytical works with this paper. So thank you. I will be happy to entertain any questions.
Wonderful. Thank you so much, Sangwon. Great talk. I guess we have one question from James Jackson. He asks, data centers are constructed across the country in part to minimize latency. How will this approach impact latency for customer workloads?
Yeah, I very much agree with the concern. I think that, to my understanding, data processing jobs are not always urgent jobs, and some of the jobs are asynchronously done. So you can wait, for example, until next day or next minute. I think that those jobs are the primary target that we are talking about here. Potentially, this type of arrangement can be done not only between PJM and CAISO. You can imagine, just like data centers located around the country, renewable energy production is happening around the country as well. So we just analyzed the case of PJM versus CAISO, but you can imagine that this can be done at the global scale much more fluidly, minimizing some of those latencies as well.
Great. Well, are there any questions from our panelists? All right. Well, thank you, Sangwon, and thank you also to all of our wonderful speakers and those of you who attended and have supported IEE over the years. And also, I would like to thank John and Mark and the IEE staff for organizing 3 days of exciting workshops around our new themes in the Institute. We have one workshop remaining. I guess Mark can do a pitch for that before we finish, but also I would like to thank Igor for his leadership in the panel. With that, I guess Mark, you can, or John.
Actually, if I could ask one question of Sangwon, I would slow it unmuting. So machine learning, takes huge amounts of energy, right? And just totally consumes modern data centers. That seems like training and these models is something that's very applicable to what you're talking about. So I would think you could have a big impact there.
Yeah, I totally agree. Yeah. The machine learning and the artificial intelligence area would be a very interesting area in a number of different ways. Not only the amount of data processing they need, also, in the end, this type of migration and sensing the weather patterns and forecasting the renewable energy generation, I think there could be an application of AI as well.
Maybe a small comment there. I think, this is, John, very true in the context of deep learning. And I think in the context of deep learning, that is a big problem. But that's just one set of mathematical algorithms that are being used. I mean, to be specific, in our group, we use very little deep learning whenever we need it, and we used, we developed our own algorithm that actually use very little energy. But I do think that's an incredibly important question, right? We shouldn't be adding to the energy load by doing artificial intelligence.
Right. Thank you. Well, anyway, I want to thank all the panelists and all the speakers, and it was a great set of discussions, and the slides and the presentations will be available. So So if you have colleagues that weren't able to attend, we typically find in these events that the ratio of downloads to participants live is 100 to 1 or more. So I think we'll have a big impact. So I'll hand it over to Mark, and I want to thank Mark for all of his organization of this workshop as well. So Mark?
Yeah, I just want to say thank you to everybody. And as John said, the recordings, the video recordings will be made available online in a few weeks after we get them all sorted out per talk. So if any particular talk you want to go back and see, you'll be able to do that. Thank you so much, Igor, Manoush, for all your leadership in putting this together. Sangwon for a great closing keynote, and all of our speakers, Gary and Sila, thanks to some of the audience members who were very active, Glenn and James Jackson, his former colleague of mine at Intel, and several of the PhD students and a number of people. So this was just a great day. So thank you very much. Please join us next week, the same time, same channel. Well, not same channel, same time, 9 to 1 on next Friday, the Food, Energy, Water Nexus workshop, for those of you interested in that. And again, thank you so much, and we'll see you again. And thanks, everybody.
Thanks, Mark.
Thank you, Gary.